Hello, I'm Marvin Timer, and I'm a distinguished engineer at Amazon Web Services. And today I want to talk about a paper that Berkeley wrote a couple of years ago entitled Cloud Computing Simplified, a Berkeley view on serverless computing. And I want to examine that paper's predictions and characterization of things from the perspective of 2 years hence. So the Berkeley paper, or the Berkeley folks in several papers, basically, I think, tried to say the following. They argued that a simplified programming environment, which is the promise of serverless, will make the cloud much easier to use. They characterized serverless computing as being a combination of functions as a service combined with backends as a service. And they predicted that this combination would make serverless use skyrocket because it would be so much better than what we've had before. But they did point out there would be some challenges. At the time, they observed that there were inadequate storage options, especially on the ephemeral side, but also on the persistent side for dealing with serverless computing functions. They observed that the serverless model provided inappropriate and unpredictable communication and coordination functionality. They also observed a number of limitations on the compute capabilities. Lambda functions had a limited time that you could run them. Startup times could be very slow depending on what code you had and so forth. And they also voiced security concerns about the multi-tenant nature of serverless computing. So let's look at their core prediction, which was that serverless computing would become popular, and that has proved to be very much true. It has become immensely popular, at least as we see it on AWS. When we look at Lambda, which is what AWS's premier serverless computing service is, we see that over half of the new applications built inside Amazon are now built with AWS Lambda. So it's very popular. We're seeing that customers of AWS are making trillions of invocations per month, so it's definitely something that's in heavy use. And we're seeing that some customers are making tens of thousands of concurrent invocations with Lambdas. So its promise of seamless scaling to huge volumes has also proven to be true. So that part has been absolutely accurate. But one thing that I think is a little more complicated than what the Berkeley folks originally characterized is this question of whether serverless equals function as a service combined with backends as a service. And what I want to argue is that life's a little more complicated and not quite as crisply clean as that. To begin with, let's think about what is a function. If we think of function as a service as meaning a Lambda function in the sense of a function that has no name so that you can't reach it, that runs for a little while and ends, you can ask, well, how does that map onto the various things that people have called serverless and that offer something similar? For example, you might compare Lambda functions to Fargate containers. Both Lambda and Fargate can say that they are serverless, but one is very much aimed at a function and another one is aimed at running a full container that typically runs for a very long time. Now, Lambda now offers the ability to define functions as containers. So in that sense, Lambda has gotten similar to Fargate. On the other hand, Fargate gets used for very different things. For one thing, most Fargate containers can run for an arbitrarily long period of time and are often used to implement long-running web services. That's not what the intent of Lambda was, but this question of what's a function becomes fuzzy here. The same thing applies when we think of things like step functions or MapReduce functions or API gateway functions. Each of these offer a model where you can define a function, much in the way that you can define a Lambda function, but it's embedded in a much larger framework or ecosystem in order to enable its use. So are these functions functions? Is this a function as a service? Or is something like step functions or an EMR cluster, is that something different? You could ask the same question about SQL queries. These are functions. On the other hand, they only have meaning inside of a relational database or in some kind of a relational model. And of course, once you have infrastructure as code, is a function that creates something as a function call, is that a function or is that resource management? These things become fuzzy. The same thing applies to backend services. S3 is a great example of what people commonly think of as a serverless backend service, a simple API with a huge amount of complexity that deals with things like state. But DynamoDB and Kinesis are also examples of services that we characterize as serverless, and yet there are modes they offer which very much involve some form of resource management. At least until recently, if you used DynamoDB, you had to manually manage the provisioned IOPS that it depends on. You could create an auto-scaling functionality on top of it that would run it, but still somebody was doing this manual management of that. Only recently has DynamoDB offered an on-demand option where everything is managed inside of DynamoDB itself. So is Dynamo serverless? Or is it partly serverless? It becomes fuzzy. Same thing with Athena versus Redshift Spectrum. Both of these characterize themselves as serverless, and yet, at least for Redshift, you have to worry about cluster size. In fact, in practice, there's always some kind of resource management with all of these systems that you worry about, at least if you think about things like SLAs and so forth. So the premise I'd like to put out is that really when people use the term serverless, what they're often thinking of is the idea of a simple uniform environment. Basically, I think the power and the attraction of serverless is that it presumes a world that is essentially flat. Everything is distance one away, so you don't worry about whether you're on the same machine, the same rack, or in the same data center. Everything is infinite. There are no limits. There's no scale up, there is no scale out concerns. Everything basically is infinite. And they, in practice, also assume that things are immortal, that nothing fails. If I get rid of the notion of immortality, then all of a sudden I deal with a lot of complexity that I think most people don't associate with serverless, which is the question of what do you retry, how do you deal with partial runs of things, and so forth. So the challenge, I would argue, is if serverless is really about simplified uniform environments, how do we make the real world appear as if it obeyed this ideal? Now the good news is oftentimes you don't care. The world is flat enough, big enough, and robust enough for your needs, and so you can simply run a serverless model and it just works. And the cost and the performance is good enough, and so everything is fine. The other bit of good news is the world is getting better. If you look at a modern cloud, it is far more flat, far more elastic, and far more robust than what we used to have. And so the class of applications for which you don't care about the fact that the world is not truly flat and infinite and immortal has gotten much larger. And of course, when you have back-end services, you can hide a lot of complexity behind those. But what I want to argue is you can't hide all of the complexity. So I want to now switch to the question of what's fundamental and what's incidental. What I want to argue is the fundamental question here is that there actually is no free lunch. The world is not flat, it's not infinite, and it's not immortal. And so what we have to think about is the question of what can we achieve, and for this I want to introduce the notion of an entitlement. You can imagine that for a given problem or in a given compute environment, like a cloud, there's a notion of what's the cheapest possible solution I could implement if I were perfect at doing this, what is the cheapest I could do? Similarly, I could ask what is the most performant solution I could come up with? And then finally, you could ask, well, how simple is it to do this? Because the challenge is in order to truly optimize cost and performance, I need to take advantage of the non-flat, not infinite, and non-immortal parts of the environment I'm computing in. And so the challenge is, it may seem, is that in order to optimize cost and performance in a complicated world, I have to give up simplicity. Or at any rate, I have to pick any two of the three. I could have cost and simplicity, but then I wouldn't have performance because I'm simply not telling you enough in order to achieve the performance. Or I could have performance and simplicity by simply buying lots of hardware. But I'm going to argue this is a false trade-off. The real question is, who has to deal with the complexity? If I, as a customer, want to have optimized cost and performance, and I can figure out somebody else to deal with the complexity, then it would seem as if I get all three. And I'm going to argue that if you figure out the right way to delegate complexity, all the other problems get solved from that. So delegating complexity, we tend to use two different approaches. One we've already talked about, which is backends as a service. This is basically delegating to other human beings. A service with a simple API that hides an enormous amount of complexity is designed, implemented, and operated by human beings. And this works awfully well. And then we use things like compilers or query and workflow planners in order to enable you to write your business logic, your functions, in something like Java or step functions or SQL. and that gets translated down to enormously complicated low-level programs. So it would seem we're done with that, right? But not really. Because the challenge is that simple interfaces have their limits if I'm not willing to tell you very much. Consider garbage collection, for example. It's very easy to write a functionally correct program with a garbage collector, but if I don't tell you anything more than simply the functional operation of the program, and I want cost and performance, it's going to become challenging. If I want cost, I may give it only enough memory in order to run, but now I'm constantly risking out of memory errors. Similarly, if I want ultimate performance, I may need to rewrite parts of the program in order to do manual memory management because garbage collectors have a cost. There's a similar kind of a problem with web services. It's very easy to write a web service. It's very hard to specify and deal with all the exception cases that can occur in a distributed system. DynamoDB is a similar thing. You can write a program that uses the Dynamo functional API very quickly, but if you manage the IOPS yourself, that becomes quite complex quite quickly. Luckily, the on-demand feature can handle this, but it isn't free. Though I'll observe that it's often cheaper to use that than to have a human attempt to do this. But the even bigger challenge is that all of these services on the back end have to play well with each other. You have impedance matching problems, for example. Consider when you asynchronously submit lambdas. These get queued up in an SQS queue and then submitted to the Lambda invoker. If SQS can't autoscale at the same rate as the Lambda invoker, now I have an impedance mismatch. Indeed, anything that is not as elastic as all the other parts of the system risks becoming a bottleneck. And if you think of retries and all of the things required for distributed systems, like dealing with poison pill requests, delegated access controls, and so forth, what you end up realizing is that instead of needing just back-end services, what you need is back-end services plus some way of coordinating things between them. You need tools and frameworks that allow you to manage the system as a whole. Now the problem is the tools that we use for that latter kind of a thing work best in well-defined environments, and unfortunately the cloud is fairly messy. It has a much larger functional interface than the kind of thing that a compiler usually targets, and the non-functional aspects of a cloud are not that well defined. Things like, for example, how it auto-scales under various circumstances. So clouds have messy complexity. What's worse is, in order to get cost optimization, you need multi-tenancy, and this introduces an aspect that is even worse. It introduces the unpredictability of noisy neighbors. And what it implies is that in order to make things work well, what you basically need is a system where all of the tenants basically tell the system enough about their applications and their workloads so that the system can figure out how to deal with them, how to manage them so that they don't get into each other's ways. And this requires that information propagate to all the relevant parts of a system. So the challenge here is how much information should a user have to specify in order to get their job done the way they want it, and who needs to know about it. Now there's an intriguing possibility that I'm only going to allude to because I don't have enough time, which is that ML-based approaches offer one possible way of dealing with this messy complexity by allowing the system to observe what is happening and learn from it without requiring that somebody explicitly tell it all about it. This is intriguing, but this represents something that is a future hope rather than something that we know how to do completely successfully right now, though it's getting better. So let's look at all the incidental challenges that were listed before. Inadequate storage options, well, we're already seeing more back-end services that are starting to deal with this. Inappropriate and unpredictable communications and coordination functionality, well, if you look at the higher level frameworks like MapReduce and so forth, I would argue that these, combined with the idea that you specify the business logic as embedded functions in those, are addressing this kind of an issue. As far as limitations on compute capability, we're seeing that micro VMs and the ability to snapshot those, access to specialized hardware, all these things are problems that are being addressed and are getting better, and I don't see any inherent reason why we can't address all of them. As far as security concerns, I actually believe that things have gotten better than before because we're moving from a world where developers write security-based code to one where operators and security engineers provide declarative configurations. Now there's one additional challenge I want to mention, which is that in an elastic world, you have to deal with potentially unbounded, unintended behavior. High elasticity means you can consume a lot of resources very quickly, and if you can invoke them asynchronously, you may not notice the problem until much later. This requires appropriate budgets and guardrails, which is another example of additional information that has to be provided by the user. So when we put it all together, I would argue that really instead of fast plus BAS, what we need is a more heterogeneous and rich system where there's function as a service, plus things like managed containers that you might be able to call to, plus managed pods of microservices, plus a variety of BAS building blocks, plus higher level constructs that allow you to put all this stuff together end to end. And of course, the big challenge going forward is, can we have the system figure this out without our having to tell them everything? So in conclusion, I think the Berkeley paper was right. Serverless has been a success and its use is skyrocketing. Life is indeed simpler, but I would argue it's gotten better, but it's not nearly as simple as it could be. And the reason why is because we have to figure out how to specify a variety of information beyond just a function that calls a bunch of back-end services. Indeed, the complexity is a question of all the complexity across things like access controls and SLAs and so forth. And so really the challenge is, how do you express all of this information in the most concise, simple form? So I would argue that instead of talking about serverless computing, what we really need to talk about is something like expressive computing, because it's about more than just servers. That concludes my talk, and I thank you for listening.